You are sitting still, reading this on a screen that feels solid, reliable, and unremarkable. Light leaves that screen, enters your eyes, and your brain quietly converts it into meaning. You have done this your entire life. You do not think about the light itself. You assume it is understood. You assume it is simple. A photon is supposed to be the most basic thing in nature. No mass, no size, no internal structure, just a carrier of energy moving through empty space. It is what makes vision possible. It is what allows the universe to be seen at all. And yet, over the last century, physicists have repeatedly encountered situations where light behaves as if it contains more than it should, as if something inside it resists our definitions, as if the simplest particle in reality is quietly violating the rules we use to describe it. This is not a story about science fiction or fringe ideas. It is a story about real equations, real experiments, and real mathematical results that have been checked, replicated, and reluctantly accepted. Results that suggest the photon may not be as empty as we think, that it may carry hidden structure, hidden motion, or hidden information that does not fit cleanly into our picture of reality. If something can hide inside a photon, then the problem is not light. The problem is how much of reality you are actually seeing. And that is the question you are about to confront. You begin with confidence. A photon has no mass, no volume, and no internal parts. It is not made of smaller pieces. It does not age. It does not slow down. In textbooks, it appears as a clean mathematical object, a point of energy moving at a constant speed. This simplicity is comforting. It suggests that at the foundation of reality, things become clear rather than complicated. You are taught that when matter is stripped away layer by layer, what remains is elegant. Atoms give way to particles. Particles give way to fields. And light, you are told, sits near the bottom of this hierarchy. It is not a composite. It is not a system. It is not something that can be taken apart. It is treated as the irreducible messenger of the universe. This belief shapes how you think about seeing. Vision feels passive. Light exists. It travels. It reaches you. You receive it. Nothing about this process suggests depth or structure. A photon leaves a source and arrives at your eye as if it were a simple delivery, a transfer of energy with no internal story. But this confidence depends on something subtle. It depends on the assumption that simplicity in mathematics corresponds to simplicity in reality. That because an equation is short, the thing it describes must be plain. That when a symbol has no subscript, no index, no internal label, the object itself must be empty of content. This assumption is rarely questioned because it works. You calculate trajectories. You predict interference. You build technologies that rely on light behaving exactly as the equations say it will. The success is overwhelming, and success has a way of silencing doubt. Yet even in this simplest description, cracks appear. The photon has energy, but no mass. It has momentum, but no rest frame. It carries angular momentum, but nothing rotates. It obeys relativistic constraints perfectly, yet resists being localized in space. These facts are usually presented as features, not problems. You accept them as quirks of the quantum world. But consider what you are actually doing. You are attributing physical properties to something you insist has no physical extent. You are describing motion without substance, rotation without structure, transfer without a carrier. Each statement is mathematically sound. Taken together, they form an object that behaves as if it has more going on than it is allowed to have. You might tell yourself that this is simply how fundamental particles are. That intuition fails at small scales. That language breaks down. And this is true to a point. But notice what this explanation avoids. It avoids asking whether the simplicity itself is an approximation, whether the photon appears simple only because you have chosen a description that hides complexity rather than revealing it. In classical physics, simplicity often emerged from averaging. A gas appears smooth because you ignore individual molecules. A solid seems rigid because you overlook atomic motion. In each case, what looked fundamental was later revealed to be collective behavior. Simplicity was not basic. It was the result of looking from far away. Quantum theory tells you the photon is fundamental, but it also tells you that what you call a particle is really an excitation of a field, a disturbance, not an object. Already, the photon is less like a thing and more like an event, less like a bead and more like a pattern. If the photon is an excitation, then the question shifts. What exactly is being excited? And what properties belong to that excitation itself versus the underlying structure that supports it? You are used to thinking that if something has no parts, nothing can hide inside it. But this only makes sense if parts are the only way complexity can exist. Fields do not follow this rule. Patterns do not follow this rule. Relationships do not follow this rule. The confidence you begin with is not unreasonable. It is inherited. It is taught. It is reinforced by every successful calculation, but it rests on an idea that has failed before, that the simplest description is the final one. The photon feels like bedrock. But bedrock has a history of turning out to be a surface. That confidence weakens the moment you examine how photons actually behave. They interfere with themselves. They pass through two places at once. They arrive as single impacts, but spread out as waves. You can predict their statistics, but not their individual actions. Already, light is not doing what a simple object should do. You expect a particle to take a path, one path, from here to there. If you block that path, the particle stops. If you open two paths, it chooses one. This expectation is not philosophical. It is practical. It comes from every object you have ever handled. But when you send photons through a double slit, this expectation collapses immediately. You fire them one at a time. There is never more than one photon in the apparatus, and yet, over time, an interference pattern forms. Bright bands and dark gaps appear, exactly as if waves were overlapping and canceling. The pattern does not emerge from many photons interacting. It emerges from single photons behaving as if they have explored both paths. You can slow the experiment down as much as you like. One photon every minute, one every hour. The result does not change. Each photon arrives as a localized impact, a single dot on a detector. But the distribution of those dots betrays a deeper structure. It reflects a wave that was never directly observed. This is not because you failed to measure carefully enough. It is because the photon does not have a definite trajectory between emission and detection. The mathematics does not allow it. There is no hidden path waiting to be revealed. The equations describe a spread of possibilities, not a concealed route. You may try to force the issue. You place detectors at the slits to see which one the photon passes through. And the moment you do, the interference pattern disappears. The photon now behaves like a particle again. It chooses one path. The wave-like behavior vanishes. This change is not gradual. There is no compromise. You either get interference or you get path information. You cannot have both. The act of asking where the photon is destroys the conditions that allowed it to behave as if it were in multiple places. This is often explained by saying that measurement disturbs the system. But this explanation is misleading. The effect does not depend on physical disturbance in the ordinary sense. Even the possibility of gaining which path information is enough. What matters is not force, but information. At this point, the idea of a particle becomes unstable. A particle is something that exists at a location, something that persists through time, something that can be tracked. The photon satisfies none of these criteria consistently, and yet it also refuses to be a wave in the classical sense. A wave spreads continuously through space. You can divide it. You can measure part of it without destroying the rest. A photon cannot be divided. When it is detected, the entire event occurs at once. There is no half photon. There is no partial arrival. You are left with an object that is neither particle nor wave, but switches between these behaviors depending on what questions you ask. This is not because light is indecisive. It is because your categories are inadequate. The deeper problem is not that photons behave strangely. It is that they behave in a way that cannot be mapped onto any familiar ontology. The photon does not exist as a thing moving through space. It exists as a set of constraints on possible outcomes. Between emission and detection, the photon is not somewhere. It is not everywhere either. It is described by a mathematical object that encodes what could happen, not what is happening. And this description evolves smoothly, deterministically, until the moment an interaction forces a result. You might try to imagine the photon as secretly taking one path while somehow knowing about the other. But experiments rule this out. You might imagine hidden variables that restore classical behavior, but decades of tests have placed strict limits on what such variables could be. The uncomfortable conclusion is that the photon does not carry a single, well-defined story through time. Its behavior is not the unfolding of a trajectory, but the resolution of possibilities. And if this is already true for how light moves through space, then the idea that it is a simple object begins to feel less like a foundation and more like a convenient fiction. To make sense of this, you are told that light is also a wave. But this wave is not made of anything. It does not ripple through a medium. It exists in equations, not in space. The photon is said to be both particle and wave, but never fully either. This is not an explanation. It is a truce. You are accustomed to waves having substance. Water waves move water. Sound waves compress air. Even seismic waves travel through rock. In every familiar case, a wave is a pattern of motion in something else. Remove the medium, and the wave vanishes. Light refuses this rule. There is no luminiferous ether, no hidden fluid filling space. Experiments destroyed that idea more than a century ago. Light propagates through vacuum as easily as through glass. Whatever is waving, it is not matter. Instead, you are given the electromagnetic field, an abstract entity defined at every point in space and time. When this field oscillates, you call it light. When it is quantized, you call the oscillation a photon. The wave is now a change in field values, not a motion of stuff. This solves one problem and creates another. A field exists everywhere. A photon does not. The field can be spread out. The photon arrives all at once. The wave picture explains interference and diffraction, but it cannot explain why detection is always discrete. Quantum mechanics resolves this by introducing the wave function. But this wave is stranger still. It does not describe energy or charge or motion. It describes probability. It tells you the likelihood of finding a photon at a particular place, if you look. This is where the wave leaves physical space entirely. The wave function does not live in the world you inhabit. It lives in a mathematical space whose dimensions correspond to possible configurations, not locations. When you draw it as a wave in space, you are already simplifying. You are told not to ask what the wave function really is. You are told it is a tool. It evolves according to precise equations and gives correct predictions. That should be enough. And for calculations, it is. But conceptually, this answer is evasive. You are using a wave to explain behavior. While insisting that the wave is not something that exists, you are relying on structure while denying substance. Consider what happens between emission and detection. The wave function spreads. It interferes with itself. It responds to boundaries and obstacles. It behaves exactly like a real wave would. But the moment you ask where the photon is, the wave vanishes, replaced by a single event. If the wave were merely ignorance about a hidden particle, this would make sense. But experiments rule this out. The interference pattern depends on the wave's existence, not on your lack of knowledge. The wave is doing real work. And yet, the wave cannot carry energy in parts. It cannot be split into fractions that arrive separately. The energy arrives in a single, indivisible unit. The wave guides the event, but is not the event itself. This division is unsettling. You are asked to accept that the wave is physically influential, but not physically real, that it shapes outcomes without being an outcome, that it exists in a sense that cannot be localized, stored, or directly observed. You might try to think of the wave as a field disturbance again, but the electromagnetic field already exists independently of photons, and the wave function is not the electromagnetic field. It is something layered on top of it, a description of possible excitations, not of the field itself. At this point, the word wave has lost its grounding. It no longer refers to motion or vibration. It refers to structure in possibility space, a pattern in what could happen, not in what is happening. The truce you are offered is this: do not demand a picture. Accept the duality. Use the mathematics. Stop asking what is really there. But this truce has a cost, because if the wave is not a wave and the particle is not a particle, then the photon is not a thing in the ordinary sense at all. It is a rule for how interactions occur, a constraint on reality, not a component of it. And if that is true, then the question of what might be hiding inside a photon becomes unavoidable, not because there is a hidden object, but because the very idea of inside and outside may no longer apply. You then learn that photons have angular momentum. They have spin. This should imply rotation, structure, or internal motion. But a photon has no size. There is nothing to rotate. And yet, the mathematics insists the spin is real. You can measure its effects. Something is happening without anything to happen in. You encounter spin as a number attached to the photon, a fixed quantity that never changes. It is not optional. It is not emergent. It is as fundamental as the photon's energy. And the consequences of this spin are physical. Polarized light twists materials. Circularly polarized photons exert torque. Angular momentum is transferred. Objects respond. In classical physics, angular momentum is inseparable from extension. A spinning wheel has parts moving around an axis. Even a point mass requires a lever arm to define rotation. Spin without size makes no sense. And yet, the photon has precisely this property. You might try to imagine the photon as a tiny spinning object, but this fails immediately. A photon cannot be brought to rest. There is no frame in which it sits still so that you can watch it rotate. Any attempt to assign a surface or radius leads to contradictions with relativity. The faster the edge would need to move, the more impossible the picture becomes. So the word spin is misleading. It does not refer to literal rotation. It refers to a representation, a way the photon transforms under rotations of space. When you rotate your coordinate system, the photon's mathematical description changes in a specific constrained way. That constraint is called spin. But notice what has happened. A property that produces physical torque is now defined entirely in terms of symmetry. Not motion, not structure, transformation behavior. This already stretches intuition. But the situation becomes stranger when you consider that photons only come with two possible spin states, left-handed and right-handed. They are tied to the direction of motion. You cannot flip a photon's spin without changing how it propagates. The spin is locked to its trajectory. This locking has measurable consequences. In curved space, in twisted fibers, in gravitational fields, the spin of light couples to geometry. The path of the photon bends slightly depending on its polarization. The effect is small, but real. The photon's internal degree of freedom responds to the shape of space itself. At this point, the spin no longer feels like a bookkeeping device. It behaves like an internal orientation, a directionality that is not spatial, but still influences motion through space. And yet, there is still no internal structure to point to, no axis, no rotating mass, no hidden wheel. The spin exists without a carrier. You might try to retreat to the field picture. Perhaps the electromagnetic field is what carries the angular momentum. After all, fields can store and transport energy and momentum, but this only shifts the problem. The photon is supposed to be a single quantum of that field. When you detect it, the field excitation disappears everywhere at once. The spin disappears with it. So where was the angular momentum stored? Not in a region, not in a rotating configuration you could isolate. It was present as a global property of the excitation, a property that had effects without being localized. This forces a reevaluation of what it means for something to have a property at all. You are used to thinking of properties as attached to objects. Mass belongs to matter. Charge belongs to particles. Spin, in this case, belongs to an event. The photon does not spin. The interaction involving the photon carries angular momentum. The property is relational. It manifests only when something else responds to it. This is why you can change the polarization of light without changing its energy. You are not altering how much of the photon there is. You are altering how it will interact, how it will couple to detectors, materials, and geometry. Spin becomes a kind of instruction, a rule embedded in the excitation that governs how it can affect the world. It is real enough to twist molecules and rotate mirrors, but abstract enough to resist visualization. And this is the deeper unease. The photon carries a property that acts like structure without having structure. It influences outcomes without occupying space. It persists across distances without residing anywhere in between. If something like spin can exist without anything spinning, then the absence of internal parts no longer guarantees simplicity. It only guarantees that whatever is there cannot be pictured. The photon remains small, massless, and indivisible. But it is no longer empty. It carries constraints, orientations, transformations, effects. And once you accept that, the idea that nothing could be hiding inside a photon begins to lose its certainty. When you rotate polarized light, you are not changing its energy or direction. You are changing an internal orientation. This orientation behaves like a property that exists independently of motion through space. The photon now seems to carry an internal degree of freedom, even though it is not supposed to have an inside. You can perform this manipulation with ordinary tools: a polarizing filter, a rotated crystal, a carefully aligned mirror. The photon enters unchanged in speed and wavelength and exits with the same measurable energy. And yet, something about it is different. The way it will interact has been altered. This difference is not subtle. Two beams of light can be identical in every classical respect and still behave differently when they meet another system, simply because their polarizations differ. One passes through. The other is absorbed. One triggers a transition. The other does not. If polarization were merely a property of the electromagnetic field in space, this might feel intuitive. But polarization remains meaningful even when you consider a single photon, isolated from everything else. One photon can be vertically polarized. Another can be circularly polarized. The distinction persists even when there is nothing to compare them to. This persistence is troubling. Orientation normally requires a reference, a direction relative to something. But the polarization of a photon is not defined by an external object. It is an intrinsic label that travels with the photon, unchanged unless acted upon. You can rotate your laboratory. You can rotate your coordinate system. The physical effects remain. Polarization is not an artifact of description. It is something the photon carries. And yet, it is not a direction in space. The photon does not point. It does not have an arrow. Its polarization lives in a mathematical space separate from position and momentum. A space of internal states. This space is small, but it is real. You can navigate it. You can superpose states. You can entangle polarization with other degrees of freedom. You can encode information in it. Entire quantum communication systems are built on this fact. At this point, the idea that the photon has no internal structure begins to feel strained. You are manipulating something internal. You are rotating something that is not the photon's path. You are changing how it will respond without touching where it is or how fast it moves. One way to dismiss this is to say that polarization is just a choice of basis, a way of describing the field. But this explanation breaks down when you perform experiments that depend on relative polarization between photons that never interact locally. Entangled photons share polarization correlations even when separated by large distances. Changing the measurement basis for one affects the outcomes for the other. Whatever polarization is, it is not confined to a single location. You might try to imagine polarization as a hidden arrow attached to the photon. But this arrow cannot exist in ordinary space. It cannot be measured directly. It only reveals itself through interaction, through consequences. This is the pattern that keeps repeating. The photon carries properties that do not correspond to physical parts, but still behave as if they are internal features, features that persist, features that can be transformed, features that can be correlated across distance. Polarization also exposes another discomforting fact. There is more than one way to describe it. Linear, circular, elliptical. These are not different physical states. They are different perspectives on the same internal space. Rotate your description, and what looked simple becomes complex. This flexibility is powerful, but it also hides something. If an internal degree of freedom can be represented in multiple incompatible ways, then no single picture captures what it really is. The structure exists, but it resists being pinned down. you are left with an object that has no size, no interior, and no components, yet supports an internal state space rich enough to encode information, exhibit correlations, and influence interactions. This is not what simplicity looks like in any other domain of physics. Polarization does not prove that something literal is hiding inside the photon, but it proves something more unsettling, that the absence of parts does not imply the absence of structure. And once structure appears where none should exist, the question changes. You no longer ask what the photon is made of. You ask what kind of thing can have an inside without having an interior at all. Photons push on objects. Solar sails move because light transfers momentum. Momentum is usually tied to mass and velocity, but the photon has no mass. The equations still work. The force is real. The transfer is measurable. The explanation is precise and deeply unsatisfying. You are taught that momentum is mass in motion. A heavy object moving slowly can carry the same momentum as a light object moving quickly. This relationship feels fundamental. It links substance to action. Something pushes because something is there. Light violates this intuition cleanly and completely. A photon has zero rest mass. It cannot be slowed down or sped up. It always moves at the same speed, and yet, when it strikes a surface, it delivers a kick. Mirrors recoil. Atoms shift. Spacecraft accelerate. This is not a theoretical curiosity. It is exploited deliberately. Solar sails rely on nothing but light pressure to change their trajectory. No fuel, no exhaust, just photons arriving and departing. The momentum transfer is small, but relentless. Over time, it accumulates. You can calculate this precisely. The momentum of a photon is given by its energy divided by the speed of light. The formula is simple. It works. It has been confirmed countless times, and it explains nothing about how a massless object can push. You might try to imagine the photon as carrying effective mass while in motion, but this is not allowed. The photon has no rest frame. There is no perspective in which it sits still and behaves like matter. Assigning it mass breaks the very symmetry that defines it. So, momentum becomes detached from substance. It becomes a property of energy itself. Something can carry momentum without carrying mass, action without inertia, influence without resistance. This already strains classical intuition, but the problem deepens when you consider conservation laws. Momentum must be conserved. When a photon is emitted, the source recoils. When it is absorbed, the absorber recoils. The accounting balances perfectly. But where is the momentum in between? Not located in a mass, not stored in a moving object with extension. It exists as a relational quantity attached to the process, not to a thing. In field language, you are told that the electromagnetic field carries momentum. Fields can store energy and momentum in their configuration. This helps, but only partially. A field is spread out. A photon is discrete. When the photon is detected, the field excitation disappears everywhere at once. The momentum does not smear out. It transfers in a single event. A click, a recoil, a shift. Once again, you encounter a property that behaves as if it belongs to an object, but cannot be located within one. The photon delivers momentum without being a mass in motion. It affects matter without sharing its constraints. This becomes especially unsettling when you consider that momentum determines motion through space. It defines trajectories. It governs collisions. If something without mass can alter momentum, then mass is not the fundamental driver of dynamics you thought it was. Momentum, like spin and polarization, begins to look less like a physical possession and more like a rule, a constraint enforced during interactions, a bookkeeping requirement imposed by symmetry, not by substance. You can change the momentum of a photon by changing its wavelength. Red light carries less momentum than blue, but this change does not involve adding or removing parts. It does not involve acceleration. It is a shift in frequency, a property of oscillation, not motion. The photon's momentum is tied to its wave-like aspect. Shorter wavelengths mean higher momentum. The push comes from oscillation, not mass transport, from periodicity, not inertia. This reverses your expectations. You expect waves to be gentle and particles to be forceful. Here, the wave delivers the punch, and yet, the wave itself is not material. It is not a vibration of a medium. It is a pattern in a field, an abstract oscillation that somehow carries the ability to move objects. At this point, the explanation becomes circular. Photons push because they have momentum. They have momentum because the equations say they must. The equations are trusted because they work. The dissatisfaction comes from what is missing. There is no picture, no mechanism, no story that connects cause to effect in the way your intuition demands. You are asked to accept that momentum can exist without mass, just as spin can exist without rotation and polarization, without orientation in space. Each time, a familiar property is stripped of its familiar support. The photon is accumulating attributes without accumulating substance. It pushes without weighing anything down. It moves things without being moved in return. If something can exert force without mass, then the line between object and influence is no longer clear. The photon begins to resemble not a thing traveling through space, but a rule moving events from one configuration to another. And that is another way in which simplicity begins to dissolve. You might assume a photon has a position, but quantum theory resists this. There is no universally accepted position operator for a photon. You can detect where it interacts, but you cannot define where it is. The photon exists as a spread-out possibility until it does not. Position feels like the most basic property an object can have. Before you ask what something is doing, you ask where it is. Location anchors existence. Without it, objects become abstractions. For massive particles, quantum mechanics complicates this, but does not erase it. An electron has a position operator. Its location is uncertain, but definable. You can write down probabilities that refer to places in space. The concept survives, even if it becomes fuzzy. For photons, this structure breaks down. Attempts to define a position operator that behaves consistently with relativity and quantum theory fail. The photon cannot be localized in the same way as matter, not even approximately, in a fundamental sense. This is not because the photon is too small or too fast. It is because the mathematical framework that works for massive particles does not extend cleanly to massless ones with spin. The very symmetries that define the photon forbid a simple notion of position. You can still detect photons. A detector clicks at a particular place and time. This feels like localization. But this event does not tell you where the photon was. It tells you where an interaction occurred. The distinction is subtle and unsettling. Between emission and detection, there is no fact of the matter about the photon's location. The theory does not describe a moving point tracing a path. It describes a field of potential interactions spread across space. You might try to recover position by narrowing the wave function, by preparing the photon in a tightly confined state. But the more you attempt to localize it, the more you disturb other properties. The frequency spreads. The polarization becomes ill-defined. The description destabilizes. This is not a technical inconvenience. It reflects a deeper incompatibility between localization and the nature of light. A photon is inseparable from its momentum, and momentum, for a massless particle, fixes the direction of motion but not the point of passage. In relativistic terms, a photon does not have a rest frame. There is no perspective in which it is stationary at a location. Any attempt to freeze it violates the structure of space-time itself. This leads to a strange asymmetry. Space can be described as a stage filled with photons, but photons cannot be described as actors occupying points on that stage. They are processes that link events, not occupants of positions. This becomes especially evident in experiments involving interference and delay. You can send a photon through an apparatus where the path length changes dynamically. The interference pattern responds as if the photon explored all options, even when those options were altered after it entered. If the photon had a definite position at each moment, this behavior would be impossible. The response suggests that the photon's description is not tied to a trajectory in space, but to boundary conditions imposed on the whole experiment. The notion of a photon traveling from A to B is a convenient shorthand. What actually exists is a correlation between an emission event and an absorption event. The theory connects these 2 points directly, without specifying a continuous story in between. This is why you can speak meaningfully about the time of arrival of a photon, but not about its time of presence at intermediate locations. Time marks interactions. Space, in this context, becomes secondary. Once again, you are confronted with a property you assumed was fundamental, quietly removed. The photon does not have a position in the way objects do. It does not persist through space. It appears and disappears in interactions. This makes the idea of something hiding inside the photon even more elusive. How can there be an inside if there is no location? How can something be contained if there is no place where it resides? But this is precisely the point where intuition misleads. Localization is a classical demand. Quantum theory does not promise that every entity will satisfy it. The photon exists as a pattern of possible interactions constrained by geometry, energy, and symmetry. It is extended without being spatially spread, present without being located, and if something is hidden within it, it will not be hidden at a place. It will be hidden in the rules that govern when and how those interactions can occur. Every time you detect a photon, you destroy it. The act of knowing where it is ends its existence. This makes the photon unlike ordinary objects, which persist through observation. Light only becomes real at the moment it disappears. You are used to measurement revealing something that was already there. You look at an object and it remains. You touch it and it continues to exist. Observation may disturb it slightly, but it does not erase it. Knowing and being are separate. With photons, this separation collapses. Detection is not passive, it is not a glance. It is an interaction so complete that the photon cannot survive it. Absorption is not a side effect of measurement, it is the measurement. When a detector clicks, the photon is gone. There is no remnant, no fragment, no lingering trace that can be examined further. The event you record is the event that ends the photon story. This forces you to reconsider what it means for the photon to be real. Before detection, the photon is described by a wave function, a mathematical object encoding possibilities. After detection, there is a macroscopic record, a mark, a current, a chemical change. Reality seems to enter only at the moment of annihilation. You might say that this is true for all quantum particles, but photons are extreme. An electron can scatter, change direction, lose energy, and continue. A photon cannot. Any interaction strong enough to reveal its presence removes it from the system entirely. This creates an asymmetry. You can talk about photons influencing things without ever seeing them directly. You infer their existence from momentum transfer, interference patterns, correlations. But the moment you actually observe one, it vanishes. So where was it before? Not in the detector, not as a particle waiting to be caught. It existed as a set of constraints on possible outcomes, as a probability amplitude that only becomes an event when forced to choose. This is often described as wave function collapse, but the term hides more than it explains. Collapse is not a physical process occurring in space and time. It is a change in description, a sudden replacement of possibilities with a fact. The troubling part is that nothing in the equations specifies when or why this replacement must occur. The equations governing the wave function are smooth and deterministic. They do not contain a trigger for collapse. Measurement enters as an extra rule, imposed from outside. You are told that the measuring device is classical, that the environment forces a definite outcome. But this explanation shifts the mystery without resolving it. At some point, a quantum description gives way to a classical one, and that boundary is not defined by the theory itself. For photons, this boundary feels especially sharp. The quantum description persists until the exact moment of detection. Then it stops entirely. There is no gradual transition, no partial collapse. One moment, there is a field of possibilities. The next, there is a click. This makes light feel less like an object and more like a question waiting to be answered. The photon exists as long as the question remains open. Once answered, it ceases to exist. You might try to imagine that the photon was always real, traveling invisibly until caught. But this picture conflicts with interference experiments, delayed choice setups, and entanglement. The behavior before detection depends on how measurement is arranged, even when that arrangement is decided later. The act of measurement does not merely reveal a property. It defines which properties can meaningfully be said to have existed at all. This is why statements about a photon's past become ambiguous. You can reconstruct a history that fits the outcome, but the theory does not commit to one. Multiple, incompatible stories can be consistent with the same detection event. The photon's reality, then, is not a continuous existence through time. It is a transition between preparation and outcome, a link between events, not a thing persisting through them. Light becomes real at the moment it stops being light. This inversion is difficult to accept because it reverses causality in subtle ways. You expect existence to precede observation. Here, observation seems to complete existence. If something is hidden inside a photon, it is not hidden as a structure carried along until discovery. It is hidden in the gap between possibility and fact, in the rules that decide when a potential becomes an event. And once you recognize that measurement does not reveal the photon, but creates the event you observe, the idea that light is a simple, self-contained entity becomes increasingly hard to maintain. Photons move through what you call empty space, but quantum field theory tells you that empty space is not empty. It seethes with fluctuations, virtual particles, and energy that cannot be removed. Light is always traveling through something you cannot see, but cannot eliminate. You instinctively picture the vacuum as absence. No matter. No radiation, no activity, a neutral background against which events unfold. This picture feels natural because it matches everyday experience. Remove the air from a container, and you call it empty. Remove all visible matter from space, and you extend the same logic outward. Quantum field theory does not allow this extension. In its description, every point in space is occupied by fields, not optional fields, fundamental ones. Even when no particles are present, these fields remain, and they cannot be turned off. The vacuum is the lowest energy state of these fields, but lowest does not mean zero. The fields continue to fluctuate. They jitter around their minimum values. These fluctuations are not noise from imperfect instruments. They are required by the uncertainty principle itself. If a field had exactly zero energy and zero variation, it would be perfectly defined. And quantum theory forbids that. So even in the absence of particles, energy briefly appears and disappears. Pairs of excitations form and vanish. These are called virtual particles. But the word virtual is misleading. Their effects are measurable. The vacuum polarizes. It bends light. It shifts energy levels in atoms. It produces forces between neutral objects placed close together. These effects have been observed, measured, and calculated with extraordinary precision. Empty space pushes back. This means that a photon is never traveling through nothing. It is always propagating through a restless background of fields that are interacting with themselves and with each other. The vacuum is not a passive stage. It is an active participant. In calculations, this background modifies the behavior of light. Photons interact with vacuum fluctuations, altering their effective properties. Their propagation is influenced by processes that do not correspond to any visible particle exchange. You are told that these interactions are small, corrections, renormalizations, subtle shifts that only appear in extreme conditions. But small does not mean irrelevant. It means hidden. It means folded into the constants you take for granted. The speed of light itself emerges from this interaction between electromagnetic fields and the vacuum. Change the structure of the vacuum, and light behaves differently. In strong fields, near massive objects, or inside exotic materials, the vacuum responds, and photons respond with it. This complicates the idea of the photon as a self-contained entity. If its behavior depends on the state of the vacuum, then it is not traveling alone. It is embedded in a medium you cannot remove. You might object that this medium is not like air or water. It does not define a preferred frame of motion. It does not resist uniform movement. Relativity remains intact. And this is true. But the absence of resistance does not imply absence of structure. The vacuum has properties. It has symmetries. It has a ground state with measurable effects. It can be distorted, excited, and modified. When a photon moves, it is an excitation on top of this background. Its identity is defined relative to the vacuum state. Change the vacuum, and the definition changes. This becomes especially unsettling when you realize that the vacuum itself is observer-dependent. Different observers can disagree on what counts as empty. What looks like vacuum to one can look like a bath of particles to another. The distinction between nothing and something becomes relative. So when you say that a photon is moving through empty space, what you really mean is that it is moving through the lowest energy configuration of fields as defined by a particular observer. This is not a neutral statement. It is a conditional one. The photon does not merely pass through the vacuum. It interacts with it continuously, even when no interaction is detected. The vacuum shapes the photon's possibilities, its fluctuations, and its response to measurement. If something is hiding inside a photon, it may not belong to the photon alone. It may be shared with the vacuum it travels through, a joint structure that only appears when you insist on separating light from emptiness. The idea of an isolated photon moving through nothing is a simplification layered on top of a much stranger reality. a reality where space is never empty and light is never alone. And once the vacuum itself becomes active, the boundary between what the photon is and what it moves through begins to blur. In calculations, photons interacting with the vacuum behave as if they are surrounded by a cloud of activity. Their properties shift slightly. Their behavior changes depending on the fields around them. The photon you measure is not the bare photon of theory. It is a dressed object. You might expect that a photon, once defined, remains the same everywhere, that a photon emitted in deep space is identical to one emitted in a laboratory. But quantum field theory does not allow this simplicity. The photon you write into an equation is not the photon that appears in an experiment. The bare photon is a mathematical idealization. It exists only in the absence of interactions. It assumes a perfectly empty vacuum and perfectly isolated fields. This object is never observed. It cannot be observed. The moment a photon interacts with anything at all, including the vacuum itself, it changes. This change is not dramatic. There is no visible halo, no detectable cloud in the ordinary sense. But mathematically, the photon becomes entangled with the fluctuations of surrounding fields. Virtual particles briefly appear and disappear around it. The vacuum responds to its presence. The photon responds in return. This mutual adjustment is called dressing. The photon becomes dressed by the vacuum. Its effective properties shift slightly. Its interactions are altered. Its propagation reflects not just its own excitation, but the structure of the background it moves through. You encounter this most clearly in precision calculations. The charge of an electron appears different depending on distance because the vacuum screens it. The same logic applies to photons. Their behavior depends on scale, environment, and field strength. The constants you use are not fixed objects. They are effective values emerging from interaction. This means that when you say a photon has certain properties, you are already referring to an average, a renormalized description that absorbs countless small interactions into a few stable numbers. The simplicity you rely on is achieved by hiding complexity. The unsettling part is that this hiding is not optional. Without it, the equations diverge. They produce infinities. The theory only works because you redefine the photon in terms of what you can actually measure. The dressed photon is the only photon that exists in practice. So what exactly is being dressed? Not a solid object, not a particle with a surface. It is an excitation of a field interacting with other excitations of other fields. The dressing is not something added on. It is part of what the photon is. You might try to imagine peeling this dressing away to reveal the true photon underneath. But this operation has no physical meaning. The bare photon is not hidden behind the dressed one. It is an abstraction that helps calculations converge. In reality, the photon is inseparable from its environment. Even in deep space, vacuum fluctuations persist. Even far from matter, fields remain. There is no place where the photon can exist in isolation. This blurs the boundary between the photon and the vacuum. The photon is not a self-contained entity moving through space. It is a localized excitation whose identity depends on the state of the surrounding fields. Change the environment, and the photon changes with it. This dependence becomes extreme in strong fields, near magnetars, inside dense plasmas, in engineered materials where light behaves as if it has mass, or slows dramatically, or splits into hybrid excitations. The photon merges with its surroundings and becomes something new. Yet you still call it a photon. The name persists even as the object transforms. This is a linguistic convenience, not a reflection of ontological clarity. The dressed photon carries with it traces of interactions that never fully occur. Virtual processes that leave no permanent record, but still influence outcomes. It is accompanied by possibilities that are never realized, but cannot be ignored. At this point, the idea of something hiding inside the photon becomes less metaphorical. The photon you observe is not fundamental. It is a composite of field interactions condensed into a single event, a bundle of relationships treated as a unit. What you call a photon is already layered, already structured, already influenced by invisible activity that never shows up directly in measurement. The dressing is not decoration. It is evidence that the photon cannot be separated from the deeper structure of reality it emerges from. And once that structure is acknowledged, the notion of a clean, empty, indivisible particle begins to dissolve completely. The photon you detect is not what the equations begin with. It is what remains after reality has finished interacting with itself. Under extreme conditions, photons can behave as if they have mass. In materials, in plasmas, and in constrained systems, light slows down and acquires inertia-like properties. The equations still call it a photon. Your intuition does not. You are told that a defining feature of the photon is that it is massless. This is not a detail. It is foundational. Masslessness explains why light always travels at the same speed in vacuum. It explains why there is no rest frame for a photon. It anchors the structure of relativity itself. And yet, the moment light enters certain environments, this defining feature begins to blur. In materials, light slows down. This is often explained casually, as if the photon were bouncing between atoms and taking a longer path. But this picture is misleading. The photon does not simply zigzag. In many cases, it no longer exists as a free photon at all. Inside a medium, light couples to collective excitations of matter, vibrations of atoms, oscillations of electrons. The result is a hybrid entity that shares properties of both light and matter. It propagates more slowly. It responds differently to forces. It behaves as if it has inertia. Mathematically, this behavior is described by assigning an effective mass. Not a true rest mass, but something that enters the equations in the same way. The excitation resists changes to its motion. It has a dispersion relation that resembles that of a massive particle. You can trap light in optical cavities and watch it behave like a particle with mass. You can cool these systems and observe collective phenomena normally associated with matter, such as condensation. Light begins to pile up, to occupy states, to behave statistically like massive particles do. In plasmas, the effect is even more direct. Photons acquire a plasma frequency. Below this frequency, they cannot propagate at all. Above it, their behavior mimics that of particles with mass. The equations governing their motion take on the same form. None of this violates fundamental theory. The photon remains massless in vacuum, but the environment reshapes the excitation so thoroughly that the distinction becomes operational rather than absolute. What matters is how the excitation behaves, not what it is called. This forces you to confront an uncomfortable idea. Mass may not be an intrinsic property in the way you assume. It may be something that emerges from interaction, something that appears when degrees of freedom are constrained. In these systems, light does not slow down because it is impeded. It slows down because it is no longer pure. It is entangled with matter. It carries with it a burden of interaction that gives rise to inertia-like behavior. The photon becomes heavy without becoming massive. This challenges the clean separation between particles with mass and particles without it. The boundary turns out to be contextual, dependent on surroundings, sensitive to structure. You might insist that these are not real photons, that once light enters a medium, it ceases to be light in the fundamental sense. But this response only pushes the problem back. The transition is smooth. There is no sharp moment where the photon disappears and something else takes its place. The same equations continue to apply, with modified terms. The same quantization persists. The same basic excitation evolves continuously into a form that behaves as if mass has appeared. If mass can emerge this way, then the photon's masslessness is not an inviolable essence. It is a condition that holds only in a specific context, an idealized vacuum. Everywhere else, light adapts. It acquires effective properties that contradict the simple picture you started with. This matters because mass is tied to inertia, and inertia is tied to resistance to change. If light can resist change, even conditionally, then it can no longer be thought of as a purely ephemeral messenger. It can accumulate. It can linger. It can behave as if it has weight. The idea of something hiding inside the photon takes on a new meaning here. What appears is not a hidden particle or structure, but a latent capacity, a potential that is revealed only when conditions allow it. The photon does not always behave as massless. It behaves as massless when nothing constrains it. When it is embedded in structure, it reflects that structure back into its own behavior. Once again, simplicity survives only in isolation. And isolation, as you have already seen, is something the universe rarely provides. The photon remains light, but under pressure, even light begins to resemble matter. Photons are supposed to have only two polarization states. Yet in certain contexts, longitudinal components appear in calculations and experiments. These modes are usually dismissed as mathematical artifacts. But they leave measurable traces. Something forbidden keeps showing up. You are taught this rule early and taught to trust it. A photon has two transverse polarization states, nothing more. No longitudinal mode. No vibration along the direction of travel. This is not a detail. It follows directly from relativity, gauge symmetry, and the requirement that the photon be massless. The rule is clean, the logic is tight, and yet the rule keeps being bent. In classical electromagnetism, longitudinal fields appear all the time. Electric fields point along directions. Charges create field lines that radiate outward, but you are told that these are not photons. They are static or near-field effects. The real photons, the ones that propagate freely, remain strictly transverse. This distinction is comforting. It preserves order. But it begins to erode the moment you examine how light behaves in constrained environments. Inside waveguides, cavities, and nanostructures, the electromagnetic field cannot arrange itself freely. Boundaries impose conditions. Certain modes are suppressed. Others are distorted. And in these situations, components of the field appear that align with the direction of propagation. Mathematically, these longitudinal components emerge naturally. They are required to satisfy boundary conditions. They influence energy flow. They alter forces. They affect how light couples to matter. You are then told to be careful. These are not true photon polarizations. They are effective descriptions, gauge-dependent terms, useful fictions. But the problem is that they do things. Atoms respond differently. Transition rates change. Forces appear that cannot be explained without accounting for these components. When light interacts with tightly confined matter, the longitudinal contribution leaves fingerprints in the data. At this point, The explanation becomes strained. You are using entities that are not supposed to exist to explain effects that clearly do. In quantum electrodynamics, the situation is even more subtle. Calculations introduce additional polarization states that cancel out in final results. They are called unphysical. They are introduced to preserve mathematical consistency and then carefully removed. But during the calculation, they are there. They propagate internally. They contribute. They only disappear after everything is summed correctly. This raises an uncomfortable question. If something must exist in the mathematics to produce the correct physical outcome, in what sense is it unreal? You might say that these longitudinal modes are artifacts of the description, not of reality. But this answer relies on a sharp boundary between mathematics and physics that the rest of quantum theory does not respect. The wave function itself is mathematical, yet you rely on it to describe real behavior. The deeper issue is that the rule forbidding longitudinal photon modes applies strictly only to free photons in idealized conditions. The moment you introduce interaction, confinement, or coupling to matter, the clean separation dissolves. The photon you actually work with is not free. It is embedded. It is constrained. It is dressed. And in these conditions, additional degrees of freedom leak into the description. You can try to insist that the photon itself remains pure and that these effects belong to the field or the medium. But this distinction becomes hard to maintain when single photon experiments show sensitivity to these modes. When individual quanta respond as if something along their direction matters. Once again, a forbidden property appears not as a blatant violation, but as a subtle residue, a trace, a contribution that cannot be eliminated without breaking the calculation. The longitudinal component behaves like a shadow of something that is not allowed to fully exist. It influences outcomes without ever becoming a detectable particle on its own. This pattern should feel familiar by now. Properties emerge where the definition says they should not. They are denied reality, yet required for explanation. They exist in the margins of theory, never promoted to full status, never fully erased. If the photon truly had no internal structure, no hidden degrees of freedom, then these modes would be unnecessary. The theory would close cleanly without them. But it does not. Instead, you are left with a framework that works only by introducing elements it insists are not real. Elements that act, interact, and then vanish from the final story. The forbidden keeps showing up because the underlying simplicity is incomplete. The photon behaves as if it has more ways to exist than the clean rules allow. These longitudinal traces are not evidence of a new particle hiding inside light. They are evidence of tension, a sign that the way you separate physical from unphysical may be a matter of convenience, not truth. And when forbidden modes leave measurable effects, the line between artifact and feature becomes dangerously thin. The photon continues to obey the rules you rely on, but it does so by skirting their edges, by allowing what should not exist to influence what does. At this stage, the question is no longer whether something forbidden appears. It is why the theory needs it to appear at all. When light travels through certain configurations, it acquires a phase that depends not on where it is, but on the path it took. This phase carries information about history, not location. The photon remembers something without storing anything. You are used to thinking of memory as something physical, a mark, a change, a state that persists because something inside an object has been altered. Memory implies storage. Storage implies structure. And structure implies an inside. The Berry phase violates this chain completely. When a photon moves through a system that changes slowly and returns to its original configuration, something subtle happens. All the familiar properties come back exactly as they were. Energy unchanged, polarization restored, direction intact. And yet, the photon is not the same. An extra phase appears, a shift that cannot be removed, a number that affects interference but leaves no other trace. The phase depends only on the path taken through a space of configurations, not on time, speed, or location. Two photons can begin in identical states, travel through different sequences of transformations, and end up indistinguishable by any local measurement. But when they interfere, the difference appears. Their histories have left a measurable imprint. This imprint is not carried as energy. It is not stored in a field strength or a spatial orientation. It is geometric. It arises from how the system was manipulated, not from where the photon was at any moment. You cannot point to a place where the memory resides. You cannot isolate a component that holds it. The photon does not carry an internal register of past events. And yet, the effect is real, repeatable, and unavoidable. This is not an experimental artifact. The Berry phase has been observed across physics, in optics, in condensed matter, in quantum computation. It appears whenever a system's parameters trace a loop in configuration space. The unsettling part is what this implies about identity. The photon's current state does not fully describe it. Two states that are locally identical can still differ globally because of how they were reached. This undermines a basic assumption that the present contains all the information needed to describe a system. Here, the present is incomplete. History matters even when it leaves no conventional mark. You might try to say that the phase is just a mathematical bookkeeping tool, but it produces physical consequences. Interference fringes shift, probabilities change, outcomes differ. The phase cannot be ignored. The photon behaves as if it carries a memory of its past without having a place to store it. Memory without memory. This forces a shift in how you think about physical properties. Not all properties are local. Not all properties are tied to parts. Some properties are relational. They exist only when paths are compared. The Berry phase does not belong to the photon alone. It belongs to the trajectory of the photon through a space of possibilities. A space you never see, but that governs outcomes all the same. This means that the photon's behavior depends on more than its instantaneous state. It depends on the structure of the space it moved through, on the constraints it encountered, on the order in which changes occurred. In ordinary motion, order matters only through forces and time. Here, order matters even when forces cancel and time scales do not. The effect is topological. It survives deformation. It cares only about loops, not details. Once again, you encounter a property that has no classical analog, no substance, no mechanism, no picture, yet it persists. If something like memory can exist without storage, then the absence of internal structure no longer guarantees the absence of internal information. Information can be encoded in relationships, not in components. The photon does not need an inside to remember. It needs only a history. This should make you uneasy, because it means that what a photon will do next cannot always be predicted from what it is now. You must also know how it arrived. The present is not enough. And if the photon can carry history without carrying anything, then the idea that it is a simple, self-contained entity becomes increasingly fragile. The simplicity applies only if you ignore the dimensions where history lives. The Berry phase is quiet. It does not announce itself. It hides in interference patterns and relative phases, but it reveals something profound. The photon is not just a messenger moving through space. It is a record of the constraints it has passed through, a trace of geometry embedded in behavior, not stored anywhere, not visible directly, but impossible to erase. At this point, the question is no longer whether the photon has hidden structure. It is whether structure itself always requires a place to hide it all. When photons become entangled, their properties are no longer individual. Measuring one instantly constrains the other, regardless of distance. The photon no longer carries its own state. It carries part of a larger structure that does not exist in space. You are used to thinking of identity as something self-contained. An object has its own properties. It can be described independently. Whatever happens to it happens locally, where it is. Distance weakens influence. Separation implies autonomy. Entanglement dismantles this picture completely. When two photons are created in an entangled state, their properties become linked in a way that cannot be reduced to shared history or hidden signals. Before measurement, neither photon possesses a definite polarization, spin orientation, or other relevant property on its own. The state belongs to the pair as a whole. You can separate these photons by any distance. Across a laboratory, across continents, across space. The separation does not weaken the connection, because the connection is not mediated through space at all. When you measure one photon, the result is not merely revealed. It is established. And in the same moment, the possible outcomes for the other photon collapse accordingly. Not because information traveled between them, but because there was never independent information to begin with. This distinction matters. No signal is sent. No energy crosses the distance. Relativity remains intact. And yet, the correlation appears instantly, as if distance were irrelevant. The unsettling conclusion is that the photons do not have separate identities. They are not two things that happen to agree. They are two access points to a single, distributed structure. You might try to imagine that each photon secretly carried instructions from the moment of creation. But experiments rule this out. The correlations violate inequalities that any such hidden instruction scheme would obey. The outcomes depend on measurement choices made after the photons have separated. This means the joint state cannot be decomposed into individual states. There is no way to assign each photon its own complete description. Any attempt to do so loses predictive power. The photons exist as a single quantum system, even when spatially apart. Space divides them physically, but not descriptively. This creates a profound tension with how you think about containment. If a photon does not carry its own state, then what does it carry? And where is that state located? The answer is uncomfortable. The state is not located anywhere. It exists in an abstract space of correlations, a space that does not map onto physical distance. Each photon carries only a fragment of this structure. On its own, that fragment is incomplete, meaningless. Only when combined with the other does the full description emerge. This is not a limitation of knowledge. It is a limitation of reality as described by the theory. The photon does not have hidden properties waiting to be uncovered. The properties come into being through measurement, constrained by the shared structure. In this sense, entanglement replaces individuality with participation. The photon is no longer an object with attributes. It is a node in a relationship. This relationship does not weaken with distance. It does not decay over time. It does not require a medium. It simply persists. You might try to rescue intuition by saying that entanglement is rare or fragile. but modern experiments routinely create and maintain entangled photons. Entire technologies depend on it. Quantum communication, quantum cryptography. These systems work precisely because the shared identity is real. Once again, something you assumed was fundamental dissolves. Identity is no longer local. Ownership of properties is no longer guaranteed. The photon cannot be fully described on its own. If something is hiding inside the photon, entanglement suggests that it may not belong to the photon alone. It may be shared, distributed, spread across systems without occupying space. The idea of an inside becomes ambiguous. What is inside one photon may partially exist inside another, no matter how far apart they are. This forces you to rethink what a particle is. A particle is supposed to be a unit, a smallest piece, something that can be isolated. Entanglement shows that isolation is conditional. The photon remains indivisible in interactions. It arrives as a single quantum, but its state can be inseparable from the state of another photon. Unity at the level of detection, plurality at the level of description. At this stage, the question of hidden structure shifts again. It is no longer about internal degrees of freedom carried within a particle. It is about structures that transcend particles altogether. The photon does not always exist as itself. Sometimes it exists as part of something larger that cannot be broken down into parts without losing what it is. And once identity itself becomes relational, the idea that the photon is a simple, self-contained messenger of reality becomes increasingly difficult to defend. The photon is not just light. It is participation in a structure that ignores distance, defies separation, and refuses to belong to a single place in the universe. By measuring photons gently, without fully collapsing their states, physicists have observed values that lie outside normal limits. These weak values are not errors. They emerge consistently from theory. The photon appears to briefly hold properties it should never have. You are used to measurement being decisive. You look, and a value appears. The system chooses an outcome. Anything else is treated as noise or uncertainty. This expectation is built into how experiments are designed and how results are interpreted. Weak measurement violates this expectation by design. Instead of forcing the photon into a definite state, you interact with it so lightly that its evolution is barely disturbed. The photon continues on. The measurement device records only a faint imprint. On its own, that imprint is meaningless, but repeated many times, a pattern emerges. What emerges should not exist. The measured values can lie outside the range of allowed outcomes. A photon can appear to have polarization greater than what is physically possible. It can seem to carry momentum in a direction it never travels. It can register negative energy densities or amplified responses that exceed any eigenvalue of the observable being measured. At first glance, this looks like a failure, a mistake, an artifact of statistics. But the results persist. They match precise theoretical predictions. They appear across different experiments, systems, and laboratories. The theory does not treat these values as anomalies. It predicts them. The explanation is subtle. Weak values are not properties the photon has in the usual sense. They arise from conditioning on both a preparation and a final outcome. You select a subset of events based on how the photon begins and how it ends, and then ask what can be said about it in between. In this narrow window, the usual rules loosen. The photon is not forced into a definite state, but it is not entirely free either. It is constrained from both sides. Past and future measurements jointly shape what can be inferred in the middle. This produces quantities that do not correspond to any single measurement outcome. They are contextual, relational, dependent on the entire experimental arrangement, and yet they are not imaginary. They influence pointer shifts. They affect interference. They leave physical traces that can be read out with sufficient care. The discomfort comes from what these values imply. The photon appears to momentarily possess properties that are forbidden by its own definition. Values that cannot be assigned to it at any instant in a strong measurement framework. You might say that these are not real properties, that they are artifacts of inference. But this response fails to explain why they produce consistent, measurable effects. The apparatus responds as if something unusual is there. Once again, you encounter a familiar pattern, a property that cannot exist according to simple rules, yet must be included to explain what happens. Weak measurements suggest that the photon's behavior between preparation and detection cannot be captured by a single, classical description. The photon is not simply in one state or another. It is constrained by incompatible conditions simultaneously. This creates a space where ordinary limits do not apply, where quantities are not bound by eigenvalues, where intuition about possession and exclusion breaks down. The photon does not permanently hold these strange properties. They do not survive detection. They do not appear in ordinary measurements. They exist only in this delicate regime, where information is extracted without resolution. This makes them easy to dismiss. But dismissal misses the point. Weak values reveal that the photon's description between measurements is richer than you are usually allowed to see. Not because the photon hides something, but because strong measurement destroys too much structure to reveal it. When you measure strongly, you collapse possibilities into a single outcome. When you measure weakly, you glimpse the structure of those possibilities themselves. And that structure does not respect the boundaries you expect. The photon, in this view, is not a carrier of fixed properties moving through time. It is a system constrained by preparation, evolution, and post-selection. Its intermediate description is shaped by all three. This undermines the idea that properties belong to the photon at all times. Instead, properties appear to be conditional statements, answers to specific questions asked in specific ways. The photon appears to briefly hold values it should never have, because those values are not owned. They are inferred from relationships between events. Weak measurements do not reveal a hidden interior. They reveal that the idea of an interior may be misplaced. What exists between emission and detection is not a list of attributes, but a structured space of possibilities that only partially overlaps with classical notions of reality. If something is hidden inside the photon, weak measurement suggests it is not a thing waiting to be uncovered. It is a pattern that only becomes visible when you stop insisting on certainty. The photon behaves impossibly only when you demand simple answers to questions that reality does not answer simply. And that may be the most unsettling result so far. Photons do not experience time in the way you do. Along their path, time does not pass. And yet, they accumulate phase, polarization changes, and interference effects. Something evolves without time progressing. You experience time as flow. Moments follow one another. Change requires duration. Cause precedes effect. This structure feels inseparable from existence itself. To exist is to persist through time. For photons, this structure collapses. According to relativity, there is no valid frame of reference in which a photon is at rest. As its speed is fixed, time along its trajectory does not advance. The proper time experienced by a photon between emission and absorption is zero. From the photon's perspective, if such a perspective can even be defined, the journey does not take time at all. Emission and absorption coincide. This alone is disorienting, but it becomes more troubling when you remember what photons actually do between these events. They interfere. They accumulate phase. Their polarization can rotate. Their probability amplitudes evolve continuously. Something is clearly changing. But if no time passes, what is changing? Phase is not a trivial detail. It determines interference patterns. It determines whether two paths cancel or reinforce each other. Phase evolution is the heartbeat of wave behavior. Without it, there would be no diffraction, no interference, no optics as you know it. Yet phase evolution is typically described as unfolding in time, oscillations per second, frequencies, periods, all temporal language. For a photon, this language becomes metaphorical. You can calculate phase accumulation along a path, and the calculation works perfectly. Change the path length, and the phase changes. Introduce a medium, and the phase shifts. Bend space with gravity, and the phase responds. But this change is not anchored to time passing along the photon's world line. It is anchored to geometry, to distance, to configuration. The evolution occurs without duration. This forces a distinction you rarely make between time as experienced and time as parameter. The equations use time as a coordinate, but the photon does not move through time in the way massive objects do. It moves through space-time in a way that collapses the temporal dimension. From your perspective, the photon takes time to travel. From the photon's perspective, if that notion is meaningful, the trip is instantaneous. And yet, its state at emission and its state at absorption are not the same. This suggests that evolution does not require experienced time. That change can be ordered without being durational. That something can transform without waiting. You might try to say that the phase evolution belongs to the field, not to the photon. That the field evolves in time, and the photon is merely a manifestation of that evolution. But this does not resolve the issue. The photon is the quantized excitation of that field. Its properties reflect the field's behavior. The phase belongs to the photon insofar as the photon can interfere, remove the phase, and the photon loses its wave character entirely. So you are left with an entity that undergoes meaningful transformation along a path that has zero proper time. This undermines a deeply held assumption that time is the medium of change. Here, change appears without time flowing. The same tension appears in polarization evolution. Light traveling through certain configurations undergoes rotation of polarization. This rotation depends on the path taken, the fields encountered, the geometry traversed. It accumulates continuously. But again, there is no internal clock ticking along the photon's path, no sequence of moments experienced by the photon itself. The evolution is real, but it is not temporal in the usual sense. It is relational. It depends on spatial configuration and boundary conditions, not on duration. This reframes the photon as something closer to a mapping between events than an object persisting through time. A rule that connects emission to absorption with constraints encoded in geometry and interaction. The photon does not age. It does not wait. It does not experience delay. Yet it carries the imprint of everything it passed through. This is not how objects behave. This is how correlations behave. If something is hiding inside the photon, it is not evolving in time the way internal processes do in matter. It is not ticking. It is not decaying. It is not progressing from past to future. It is structured across the path itself. The photon's history is not a sequence of moments. It is a set of constraints imposed by the entire experimental arrangement. Change is encoded spatially and relationally, not temporally. This forces a reconsideration of what internal means. Internal does not necessarily imply a private timeline. It may imply a dependence on structure rather than duration. The photon evolves without experiencing time because its evolution is not something that happens to it. It is something defined by the conditions under which it connects two events. Once again, a familiar category fails. Time, like position and mass, ceases to behave as a universal backdrop. The photon exists outside the flow you inhabit, and yet it carries the consequences of change. Something evolves without time progressing, and that something is central to how you see the universe at all. Much of the photon's description depends on gauge choices, mathematical freedoms that do not change predictions. But these choices shape what you call real and what you dismiss. The line between physical structure and mathematical convenience becomes thin. You are told early that gauge freedom is a kind of redundancy, a feature of the mathematics that allows multiple descriptions of the same physical situation. Change the gauge, and nothing observable changes. The physics remains the same. Only the bookkeeping differs. This reassurance is important. It allows you to ignore large parts of the formalism without fear. It tells you that some elements of the equations are not real, only representational. You are permitted to discard them, but this permission comes at a cost. Gauge freedom means that the photon cannot be fully described by quantities that are directly observable. Potentials appear in the equations, not just fields. These potentials can be changed without altering measurable outcomes, and yet they are essential for writing the theory down at all. In classical electromagnetism, you are taught to focus on electric and magnetic fields. Potentials are introduced as a convenience, a way to simplify calculations, something you can always gauge away. Quantum theory removes this comfort. In quantum mechanics, potentials acquire direct physical significance. They influence phase. They alter interference patterns. They affect outcomes even in regions where the fields themselves vanish. The famous example is unavoidable. A charged particle can be influenced by a potential in a region where no force acts. The photon, as the quantum of the electromagnetic field, inherits this ambiguity. Its description depends on objects you are told not to take literally, yet cannot do without. You are allowed to choose a gauge. You are allowed to remove certain components. Longitudinal and scalar parts of the field can be transformed away. They are labeled unphysical. You are instructed not to worry about them, but these components do not vanish from the mathematics. They cancel. They conspire. They appear and disappear in intermediate steps. The final answer works only because of delicate balances between terms you were told do not correspond to reality. This raises a quiet question. If something must exist mathematically to ensure the correct physical outcome, in what sense is it unreal? You might say that reality is defined by observables alone. Only gauge invariant quantities count. Everything else is surplus structure. But this definition is itself a choice, a philosophical one, not a physical necessity. Gauge freedom tells you what you are allowed to ignore. It does not tell you what exists. When you change gauges, the picture of the photon changes. Its description can look local or non-local. It can appear to have certain components or not. The same physical predictions emerge, but the internal story differs. This flexibility is powerful, but it also hides structure. It allows you to flatten complexity into equivalence classes. to declare different descriptions the same without asking what they might be describing. The photon lives inside this ambiguity. Its properties are not fixed objects, but features that survive all allowed transformations. Everything else is declared redundant, but redundancy relative to what? The danger is subtle. When you rely too heavily on gauge freedom, you begin to mistake convenience for ontology. You assume that what can be transformed away has no claim to reality, that only what remains invariant deserves to be taken seriously. History suggests this assumption is risky. Time and again, structures first dismissed as mathematical artifacts later revealed deeper principles. Coordinates, fields, curvature. What was once optional became essential when the framework expanded. Gauge freedom may be telling you not that certain structures are unreal, but that they are not individually observable. They may belong to a deeper level of description where observability is not the primary criterion. For the photon, this matters because many of its strange features live precisely in this ambiguous zone: phase, potential, longitudinal components. These are the places where gauge freedom operates. When you say that the photon has no internal structure, part of what you mean is that any apparent structure can be gauged away. But this is a statement about description, not about existence. You are choosing to ignore what the theory allows you to ignore. That choice keeps calculations clean. It also keeps certain questions unasked. The line between physical structure and mathematical convenience becomes thin because the theory itself does not mark it clearly. It gives you rules for prediction, not a map of what is real. The photon fits perfectly into this ambiguity. It behaves as if it has internal features that influence outcomes. Yet those features can be reshuffled, redistributed, or erased by a change of gauge. This does not mean the features are illusions. It means they are not anchored to a single picture. If something is hiding inside the photon, gauge freedom ensures that you will never see it directly. It will always be possible to move it somewhere else in the mathematics, to relocate it, to disguise it as redundancy. The photon may not conceal structure in the way objects do. It may conceal it in the way descriptions do. And that possibility is harder to confront because it suggests that the limits of what you can say about light are set not only by nature, but by the language you have chosen to describe it. Photons transmit information, but they do not carry bits the way objects carry cargo. The information is encoded in relationships, correlations, and constraints. It exists in form, not in matter. You instinctively picture information as something that must be stored somewhere. A mark on a surface, a state of a system, a configuration that persists because a physical substrate holds it in place. Information, in this view, always has a body. Photons challenge this assumption. When light transmits information, nothing tangible is transported from sender to receiver. No symbol rides along inside the photon. No packet is carried from point to point. What arrives is an interaction, not an object containing a message. Consider a single photon used to transmit a binary choice. Its polarization is prepared in one of two orientations. When it is detected, the orientation is revealed. Information has been transferred. But at no point did the photon carry a tiny label saying 0 or 1. The information existed in the relationship between preparation and measurement, in the constraints imposed on how the photon could interact, not in a stored token moving through space. This distinction matters because it breaks the analogy between information and matter. Matter carries properties by having them. Information is conveyed by restricting possibilities. A photon prepared in a particular state limits the outcomes that can occur when it is measured. That limitation is the message. Nothing else needs to be present. This becomes clearer in quantum communication. Entangled photons can transmit correlations without transmitting any usable information on their own. Each individual photon looks random, meaningless. Only when outcomes are compared does structure emerge. The information is not located in either photon. It exists in the pattern that relates them. You can separate the photons by any distance. The pattern persists. The information does not travel through space in the usual sense. It is instantiated only when measurements are brought together. This is deeply counterintuitive. You expect information to be something that moves, something that flows. Here, information appears without motion, without transport, without storage. The photon does not contain the message. It participates in a protocol that generates the message when conditions are met. Even in classical optics, this logic holds. Interference patterns encode information about path differences, phase shifts, and geometry. The pattern reveals information about the setup, not about any individual photon's journey. Remove the relationships, and the information vanishes. This reframes what it means to say that light carries information. Light does not deliver content. It enforces constraints. The photon is a mediator of structure, not a container of symbols. This should unsettle you, because it undermines the idea that information must always have a physical embodiment. Here, information is not a thing. It is a difference, a distinction that only appears when possibilities are compared. You might try to argue that the photon's internal state is the physical embodiment, polarization, phase, timing. But these states are not bits in the classical sense. They are not discrete units that persist independently of context. Change the measurement basis, and what counted as information disappears or transforms. The same photon can encode different messages depending on how it is interrogated. This means the information was never intrinsic. It was conditional. The photon did not carry meaning. Meaning emerged from interaction. Once again, the absence of substance does not imply the absence of effect. Information moves the world. It controls machines. It encrypts messages. It triggers decisions. And photons are among the most effective carriers of it. But they do so without transporting anything you can point to. If something is hiding inside the photon, information suggests it is not a payload. It is not a stored message waiting to be opened. It is a pattern of constraints that only becomes visible when the right questions are asked. The photon enforces rules. It limits outcomes. It shapes correlations. That is how information is transmitted. This makes the photon less like a courier and more like a rulebook that only becomes legible during interaction. You do not receive information from the photon itself. You receive it from the way the photon restricts what can happen next. This inversion matters because it means that looking for hidden content inside the photon is the wrong approach. There is nothing inside to find. The information exists in the structure of reality that the photon participates in. And once information no longer requires substance, the line between physical and abstract begins to blur. Information becomes a fundamental feature, not of objects, but of relationships. The photon, in this sense, is not a thing that carries meaning. It is a mechanism by which meaning can arise. Light does not bring you messages from the universe. It shapes the conditions under which messages can exist at all, and that makes the simplicity of the photon even more deceptive. In modern physics, the photon is not fundamental. The electromagnetic field is. The photon is an excitation, a quantized disturbance. If something hides inside the photon, it may belong to the field itself, not to the particle you see. You are accustomed to thinking in terms of objects. Even when you accept that particles behave strangely, you still imagine them as the basic units of reality, small things that exist, move, and interact. The photon fits awkwardly into this picture, but the picture persists. Modern physics quietly removes the foundation from under it. In quantum field theory, particles are not primary. Fields are. Every type of particle corresponds to a field that exists everywhere, at every point in space and time. The electromagnetic field is always present. What you call a photon is a localized excitation of that field, a momentary disturbance that can be created or destroyed. This reverses the hierarchy you instinctively assume. The particle is not the thing. The field is the thing. The particle is what the field does under certain conditions. An excitation is not an object in the usual sense. It does not exist independently of the system it belongs to. A wave on the surface of water is not a separate entity from the water. It is a pattern the water temporarily supports. The photon is more like that wave than like a bead moving through space. If this is the case, then asking what is inside a photon may be like asking what is inside a ripple. There is no interior substance to inspect. The structure belongs to the medium, but the electromagnetic field is not a substance you can point to. It has no material carrier. It does not consist of smaller parts. It is a mathematical entity that assigns values to every point in space-time, and yet it is the most empirically successful structure in all of physics. The field can store energy. It can carry momentum. It can interact with other fields. It can fluctuate even in its lowest energy state. It is real in every sense that matters experimentally. The photon inherits all of this complexity. When you describe a photon as simple, you are compressing the behavior of an infinite dimensional field into a single quantum event. You are replacing a rich, continuous structure with a discrete label. That compression hides detail by design. The excitation does not contain the field. The field contains the excitation. This matters because many of the strange properties you have encountered do not belong naturally to particles, but to fields. Non-locality, gauge freedom, vacuum fluctuations, topological phases. These are field-level phenomena. They appear puzzling only when you try to attribute them to particle interiors. When you say that a photon has no size, no interior, no structure, what you are really saying is that the excitation itself has no internal parts, but the field it excites has structure everywhere. The photon draws from that structure when it interacts. Its polarization reflects the field's degrees of freedom. Its phase evolution reflects the field's geometry. Its entanglement reflects the field's capacity to support correlated excitations across distance. The simplicity of the photon is borrowed. It is the simplicity of a label applied to something deeper. You might try to imagine isolating a photon completely from the field, but this is impossible. The photon is the field, temporarily doing something. There is no separation. Even the vacuum, which you might think of as the absence of photons, is still the electromagnetic field in its ground state. Fluctuating, structured, active. So when you detect a photon, you are not catching a particle that was traveling through empty space. You are witnessing a localized transition in a field that never stopped existing. The photon appears, interacts, and disappears. The field remains. If something is hiding, it is not hiding inside the photon as an object. It is hiding in the field's structure, which the photon samples but does not exhaust. This reframes the entire question. The photon is not a container. It is an event, a manifestation, a brief expression of something far larger and more complex. Looking for hidden structure inside the photon may be like looking for hidden gears inside a note played on an instrument. The structure is real, but it belongs to the instrument, not the sound. The electromagnetic field is the instrument. The photon is the note. And once you accept that, the unsettling possibility becomes clear. The photon may seem simple, not because it is simple, but because you are only hearing a single note from a symphony of structure you do not directly perceive. What you see is the disturbance. What you do not see is the medium that makes it possible. The photon does not hide complexity within itself. It reveals just enough of the field beneath it to let you interact with a universe far deeper than the particle you thought you understood. Quantum fields do not live only in space and time. They exist in abstract spaces of configurations and possibilities. A photon may appear simple in 3 dimensions while being complex in a space you never perceive. You instinctively assume that if something exists, it exists somewhere. That its complexity must fit inside the 3 dimensions you move through. Length, width, height. Perhaps time as a 4th. Anything beyond that feels abstract, optional, mathematical. Quantum fields do not respect this boundary. The electromagnetic field is defined at every point in space-time, but its full description does not live there. To describe what the field can do, you must specify more than values at locations. You must specify how those values can vary, combine, and interfere. You must describe an entire space of possibilities. This space is not physical in the ordinary sense. You cannot point to it. You cannot move through it. But the field evolves within it all the same. When you quantize the field, this abstract space becomes essential. States of the field are not points in space. They are vectors in a configuration space whose dimensions correspond to every possible way the field could be excited. Even a single photon occupies this space. In ordinary space, the photon appears minimal. No size, no interior, 2 polarization states, a direction of motion. It feels almost empty. In configuration space, it is not. The photon state includes information about momentum distributions, polarization superpositions, phase relations, and correlations with other fields. Each of these corresponds to a dimension in a space you never experience directly. What looks simple from your perspective may be richly structured from the fields. This is why many of the photon's properties resist visualization. You are trying to compress a high-dimensional object into a low-dimensional picture. The loss of information is unavoidable. When you draw a wave propagating through space, you are projecting a complex state down into 3 dimensions. When you imagine a particle traveling along a path, you are discarding almost everything that defines the state. The photon does not live in your space, it intersects it. This becomes especially clear in multiphoton systems. The state of 2 photons does not live in twice the space of 1 photon. It lives in a space whose dimensionality grows exponentially. Each additional photon multiplies the number of possible configurations. This growth is not a technical artifact. It is where the correlations, entanglement, and interference live. It is where quantum behavior actually happens. When photons interfere, the interference is not occurring in physical space alone. It is occurring in configuration space, where paths, phases, and possibilities overlap. The pattern you see on a screen is a shadow of that overlap, a projection of a high-dimensional structure into a surface you can look at. This means that asking whether something is hiding inside a photon may be a category error. The structure may not be inside in any spatial sense. It may exist in dimensions you never encounter. You are accustomed to thinking that if something cannot be located, it cannot be complex. But complexity does not require location. It requires structure. Configuration space has structure. It has geometry. It has topology. Paths through it can loop, twist, and interfere. Phases can accumulate. Constraints can bind states together across distance. The photon participates fully in this space. Its simplicity in 3 dimensions is misleading. It is the simplicity of a projection, not of the underlying object. This also explains why so many of the photon's properties appear contextual, why they depend on measurement setup, boundary conditions, and global configuration. You are probing different slices of the same high-dimensional structure. Change the question, and you access a different projection. Nothing new is added. Nothing hidden is revealed. You are simply looking at a different shadow. This reframes the discomfort you have felt throughout. The photon is not behaving strangely. You are insisting on describing a high-dimensional phenomenon using low-dimensional intuition. When the field has more dimensions than space, simplicity becomes an illusion produced by perspective. If something is hiding inside the photon, it is not tucked away like a mechanism. It is spread across dimensions that do not correspond to positions or directions. The photon is not small because it lacks structure. It is small because most of its structure does not live where you can see it. You interact with only a thin slice of what the field is doing. That slice is enough to light your world, transmit information, and reveal the universe. But it is not enough to show you the full architecture beneath. The photon feels simple because you meet it at the intersection between your space and a much larger one. And that intersection is all you ever perceive. Every attempt to picture a photon fails. It is not a dot, not a wave, not a spinning object. Your brain insists on images. The mathematics refuses to supply one. Whatever the photon is, it does not fit inside human intuition. You rely on visualization to understand the world. You picture trajectories, shapes, motions. Even abstract ideas are grounded in images borrowed from experience. This habit works because most of reality, at human scales, cooperates. The photon does not. When you try to picture it as a particle, it slips away. A particle should occupy a location, trace a path, persist through time. The photon does none of these consistently. Any attempt to draw its trajectory conflicts with experiments that show it exploring multiple paths at once. When you try to picture it as a wave, the image also fails. A wave should spread continuously, carry energy gradually, be divisible. The photon arrives in a single, indivisible event. It deposits all its energy at once. There is no half-arrival, no partial impact. You switch between pictures, hoping that each captures part of the truth. Particle here, wave there. But these are not complementary views of the same thing. They are incompatible metaphors that work only when applied selectively. Your intuition keeps asking what the photon really looks like. The mathematics answers by refusing the question. Quantum theory does not describe objects in space the way classical physics does. It describes states, abstract entities defined by relationships, symmetries, and probabilities. These states do not resemble anything you have seen. When physicists draw diagrams, they are not showing you what exists. They are showing you how to calculate lines, vertices, arrows. These are bookkeeping devices, not pictures of reality. This creates a quiet tension. You are asked to believe in something you cannot imagine. to accept that the most accurate description of light resists representation. This is not a temporary limitation, it is structural. Every attempt to force the photon into a picture introduces contradictions. Give it size, and relativity breaks. Give it a path, and interference disappears. Give it a spinning interior, and infinities appear. Every intuitive move costs you something essential. So, you are left with symbols. Operators, states, amplitudes. They predict outcomes perfectly. They tell you what will happen. They do not tell you what is happening. This is unsettling because it suggests that understanding, in the visual sense, may not be available at the foundations of reality. You are not failing to imagine the photon because you lack creativity. You are failing because the photon is not the kind of thing that can be imagined. This does not mean it is unreal, quite the opposite. It means that reality at this level does not share the structure of human perception. The mathematics does not translate into pictures because there is no picture to translate into. This realization forces a choice. You can insist on intuition and accept incorrect explanations, or you can accept the mathematics and let intuition fall behind. Physics has chosen the latter. The cost of that choice is discomfort. The benefit is accuracy. The photon sits at the boundary where your cognitive tools stop working, where words like inside, motion, shape, and location lose their footing, where explanation becomes prediction without picture. This is why debates about what the photon really is never resolve. Every proposed image smuggles in assumptions that the theory explicitly rejects. The photon is not hiding behind a veil waiting to be revealed by a better microscope. It is hiding behind the limits of the concepts you use to think. If something is hiding inside the photon, it is not an object you could visualize even if you found it. It would be a structure defined by relationships, constraints, and symmetries that have no sensory analog. The failure of visualization is not a flaw in the theory. It is a signal. It tells you that the universe does not owe you intuitive pictures, that the deepest layers of reality may be fundamentally non-visual. You see the effects of photons everywhere. Screens glow, stars shine, detectors click. But the thing doing the work remains inaccessible to imagination. Light illuminates everything except itself, and the more precisely you understand it, the less it resembles anything you can picture at all. You rely on technologies built on light. Lasers, fiber optics, quantum communication. They function perfectly, even though their foundations remain conceptually unresolved. Reality does not wait for understanding. You wake up to screens illuminated by photons you do not fully understand. Data moves through fiber optic cables as pulses of light guided with extreme precision. Lasers cut, measure, synchronize, and stabilize systems across science and industry. None of this is experimental. It is routine. It works. And yet, if you ask what light is doing while it works, the answers become hesitant. The laser is one of the most precisely engineered devices in history. Its operation depends on quantum coherence, stimulated emission, and phase stability. The equations predict its behavior with astonishing accuracy, but the conceptual picture underneath remains fragmented. Inside a laser cavity, photons are said to be in phase. They are described as occupying the same quantum state. But what does that mean in physical terms? Are they synchronized oscillations? Are they correlated events? Are they excitations of a field locked into a collective mode? All of these descriptions are used. None of them is complete. The device functions because the mathematics is correct, not because the ontology is settled. The same is true for fiber optics. Light propagates through glass by total internal reflection, guided by differences in refractive index. You can calculate losses, dispersion, and bandwidth with precision. Entire global infrastructures depend on these calculations. But what is actually propagating through the fiber is not a stream of particles bouncing between walls. It is not a wave sloshing through a tube. It is a guided excitation whose nature depends on boundary conditions, field modes, and quantization. The practical picture works. The intuitive picture does not. Quantum communication pushes this tension further. Protocols rely on single photons, entanglement, and interference. Security is guaranteed by the structure of quantum theory itself. Eavesdropping is detectable not because of technological limits, but because of how measurement alters states. These systems are deployed in the real world. They exchange keys. They verify identities. They operate reliably. And yet, the underlying concepts remain unresolved. What exactly collapses when a photon is measured? Where entanglement resides? Whether information travels or correlations simply appear? The experiments do not wait for answers. You can build a device that depends on non-local correlations without agreeing on what non-locality means. You can exploit phase without agreeing on what phase is. You can manipulate photons without being able to say what they are. This is not a failure of engineering. It is a feature of modern physics. The theory tells you how to calculate outcomes. It does not tell you what exists between preparation and detection. It gives you rules, not stories. And those rules are enough. This creates an unusual situation. In most areas of human knowledge, explanation precedes application. You understand a mechanism, then you use it. With light, this order is reversed. Application outruns explanation. You are surrounded by functioning systems built on concepts no one fully agrees on. This should unsettle you. Not because the technology is unreliable, but because it reveals something about reality itself. The universe allows you to manipulate it without revealing its internal logic. Understanding is optional. Consistency is not. The photon behaves in ways that resist visualization, resist narrative, and resist ontology. But it does so consistently, predictably, reliably. This consistency is enough to build a world. You might be tempted to believe that explanation will eventually catch up, that a deeper theory will arrive and make everything intuitive again. History offers little comfort here. Each deeper theory has tended to move further away from common sense, not closer. Fields replaced particles. Probability replaced determinism. Geometry replaced force. Each step increased accuracy while reducing intuition. Light has always led this retreat. From wave to particle to field to excitation to information carrier, each conceptual shift solved problems and created new ones. Each allowed technology to advance while understanding fragmented further. The fact that experiments work without explanation is not temporary. It may be fundamental. Reality does not require that you understand it in order to use it. It only requires that you respect its rules. And the rules governing light are clear enough to be exploited, but not clear enough to be made comfortable. This leaves you in an unfamiliar position. You trust devices whose operation depends on entities you cannot picture. You rely on photons behaving in ways you cannot narrate. Light works. Your understanding lags behind. If something is hiding inside the photon, it is hiding well enough that you can build an entire technological civilization without ever finding it. The universe allows this. It offers function without clarity, power without comprehension. Reality does not wait for understanding. It proceeds, indifferent, to whether the stories you tell yourself about it make sense at all. The equations describing photons are among the most accurate ever written. They predict outcomes to extraordinary precision, and yet they describe something you cannot clearly say exists in the way you think it does. You are accustomed to equations being approximations, useful tools that capture part of reality while leaving room for intuition to fill the gaps. In most domains, the math simplifies, idealizes, smooths over details you know must be there. With photons, the opposite happens. The equations are not rough sketches, they are exacting. Quantum electrodynamics predicts experimental results to more decimal places than almost any theory in history. Measurements agree with calculations to parts per trillion. No alternative framework comes close. This level of success leaves little room to argue with the mathematics. And yet, when you ask what the equations are actually describing, clarity dissolves. The symbols refer to fields, operators, states, amplitudes. They evolve according to strict rules. They produce probabilities, correlations, and conserved quantities. They tell you how outcomes relate to one another. They do not tell you what is happening. The discomfort arises because the equations work without committing to an ontology you can recognize. They never say where the photon is. They never say what it is made of. They never say what exists between emission and detection. They remain silent on precisely the questions your intuition demands answers to. Instead, they offer consistency. You might expect that such accuracy would force a clear picture to emerge. That truth would become visible through precision. But here, precision replaces picture. The more exact the equations become, the less room there is for interpretation. Every attempt to add an intuitive story on top of the mathematics introduces contradictions. You can have particles with trajectories, or you can have interference. You can have local properties, or you can have entanglement. You can have collapse as a physical process, or you can have unitary evolution. You cannot have all of them at once. The equations themselves remain agnostic. They do not privilege one story over another. They only constrain outcomes. This leaves you in an unusual position. You are confident in predictions, but uncertain about existence. You know what will happen, but not what is. In most sciences, explanation and prediction reinforce each other. Here, they pull apart. You might say that this is a limitation of language. That reality is doing something perfectly well-defined, but you lack the words to describe it. This may be true, but it does not remove the unease. Because the mathematics is not vague. It is exact. It is complete, in the sense that it tells you everything you can know operationally. And still, it does not resolve the question of what the photon is. This suggests a possibility you are rarely invited to consider. That existence itself may not be a primitive concept at the fundamental level. That asking what something is may be the wrong question. The equations describe relations between measurements. They connect preparations to outcomes. They map correlations across space and time. They do not describe objects persisting independently of interaction. The photon appears in the mathematics not as a thing, but as a rule governing how certain interactions unfold. This is difficult to accept because you want the world to be made of things. Things that exist whether you look or not. Things that have properties regardless of context. The equations do not guarantee this. They guarantee consistency. They guarantee probability conservation. They guarantee symmetry. They guarantee that when you perform an experiment, the outcomes will obey strict patterns. They do not guarantee that there is a picture behind those patterns. The discomfort deepens when you realize that no experiment has ever contradicted this framework. Every refinement has reinforced it. Every anomaly has been absorbed. The theory grows more precise, not more intuitive. You are left trusting a mathematical structure that refuses to become a story. This is not because physicists have failed to interpret it. It is because every interpretation that tries to make the photon into a familiar kind of thing must add assumptions the equations do not require. The mathematics does not need an image. It does not need a narrative. It functions perfectly without them. And that may be the most unsettling truth of all. The photon behaves as if it exists, yet resists being described as something that exists in the way you expect. The equations describe behavior without ontology, action without substance, change without a carrier. They work because they do not answer the questions you keep asking. If something is hiding inside the photon, the mathematics is indifferent to it. It neither confirms nor denies it. It simply constrains what can happen. The discomfort comes from realizing that mathematical truth may not translate into conceptual comfort. That understanding, at this level, may mean accepting rules without reasons, predictions without pictures. The equations are silent where intuition demands answers, and their silence is not a flaw. It may be telling you that the universe is under no obligation to make sense in the way you want it to. The photon obeys the mathematics perfectly. Your unease is not its problem. If the photon carries hidden structure, hidden motion, or hidden relationships, then perception itself is built on something incomplete. You do not see reality directly. You see what light allows you to reconstruct. You have always trusted vision as a direct channel to the world. Light reflects, enters your eyes, and delivers a faithful report of what exists. Distortions are blamed on lenses, shadows, or limitations of the senses, not on light itself. Light is treated as neutral, transparent, honest. But if light is not empty, neutrality disappears. Every image you form depends on photons behaving in ways you do not perceive. Phase relations you never notice. Polarization states you do not register. Correlations you cannot access. Your visual system collapses this complexity into color, brightness, and shape. What remains feels immediate and complete. It is not. If the photon carries structure that does not map onto space, time, or classical properties, then every act of seeing is already a projection, a reduction of something richer into something manageable. You do not receive reality. You receive an interface. This is not a failure of biology. It is a constraint imposed by physics. Your eyes respond to energy deposits. Your brain reconstructs edges, motion, depth. Nowhere in this chain is there access to the full quantum description of light. The information you receive has already been filtered by interactions that erase most of what the photon was capable of expressing. You see outcomes, not processes. If light contains hidden relationships, entanglement, phase history, field correlations, then perception discards them by necessity. Vision is a measurement, and measurement destroys structure. What you experience is what survives collapse. This means that the world you see is not the world as it is. It is the world as it can be mediated by light under the rules of interaction that favor stability over completeness. Objects appear solid because countless photons interact with them in constrained, repeatable ways. Space appears continuous because the phase information that could reveal discreteness is averaged out. Motion appears smooth because interference effects cancel at macroscopic scales. Your reality is the low-resolution image produced by light after complexity has been stripped away. This has consequences beyond optics. If light is the messenger through which you access the universe, and that messenger carries hidden structure you cannot decode, then your knowledge of the world is fundamentally indirect. Not because your senses are weak, but because the medium itself is selective. You never see what light is doing. You only see what it leaves behind. This challenges a deep assumption that perception, given enough refinement, could approach truth. That better instruments and sharper measurements could eventually reveal the world as it really is. But instruments also rely on light, or on fields that behave in similarly constrained ways. They too collapse structure to extract outcomes. Increasing precision does not remove mediation. It intensifies it. The more carefully you observe, the more violently you force reality into a form you can record. If light is not empty, then every observation is a negotiation, a compromise between what exists and what can be made visible. Reality offers structure. Measurement accepts only a fragment. This does not mean the unseen structure is irrelevant. It governs what outcomes are possible. It shapes correlations. It constrains evolution. It determines what can and cannot appear, but it does not appear itself. You live in a world reconstructed from shadows cast by interactions you do not witness. This realization should make you cautious about claims of direct access to reality. You are not looking through a window. You are interpreting signals processed through layers of physics that do not prioritize transparency. If something is hiding inside the photon, it is hiding in plain sight. Not because it is rare or exotic, but because the act of seeing erases it. Light does not lie, but it does not tell the whole story. Your experience of the universe is built on what survives contact with detectors, retinas, and neural circuits. Everything else is filtered out, not by ignorance, but by necessity. This does not diminish the power of science. It clarifies its limits. You can predict outcomes with extraordinary accuracy. You can manipulate reality with precision, but what you reconstruct is always a reduced version of something deeper. If light is not empty, then the emptiness you perceive between objects is not absence. It is unreported structure. And if perception itself is built on this reduction, then certainty becomes a local achievement, not a global one. You do not see reality directly. You see what light, constrained by its own hidden complexity, allows you to see. You are left with a problem that does not resolve. If something can hide inside a photon, then simplicity is an illusion. And the most basic messenger of reality may already be telling you that the universe is deeper, stranger, and less accessible than you assumed. You began with confidence. Light felt like the last place to look for mystery. It was supposed to be the cleanest element of physics, the simplest carrier, the thing that reveals, not the thing that conceals. Now that assumption no longer holds. At every step, what looked elementary turned out to be conditional. Properties without substance, change without time, information without storage, identity without individuality, structure without location. Again and again, the photon behaved as if it were more than it was allowed to be, without ever becoming something you could point to. Nothing broke, no experiment failed, no contradiction appeared. The theory remained intact. That is what makes this difficult to dismiss. The discomfort does not come from error. It comes from coherence. The photon obeys the rules perfectly. It just refuses to fit inside the story you want to tell about it. You are tempted to resolve this by saying that there is nothing hiding inside the photon after all, that the language of hiding is misleading, that what you have encountered is not hidden structure, but misapplied intuition. This response is partly correct, but it does not restore comfort. Because even if nothing is hiding inside the photon in a literal sense, something is undeniably absent from your understanding. The photon does not give you an object to hold on to. It gives you a set of rules that work without explanation. And this forces a deeper question, not about light, but about reality. If the simplest thing you know cannot be made simple, then what does simplicity mean? If the basic unit of perception resists description as a thing, then what is the world made of? The photon does not tell you that reality is unknowable. It tells you something more precise, that reality is accessible only through constraints, correlations, and outcomes, not through inspection of internal machinery. You do not learn what exists by looking inside things. You learn what can happen by observing how events relate. This is a profound shift. It means that the universe may not be built from objects with hidden interiors, but from processes with rules, from structures that exist only in interaction, from patterns that never appear all at once. The photon, in this view, is not a message from reality. It is a boundary condition, a way reality limits what you can observe while still allowing prediction. You can measure light endlessly. You can refine your experiments. You can increase precision by orders of magnitude. And still, the core question remains untouched. What is the photon when it is not being detected? The theory does not answer. It does not need to. This is why the question cannot be unasked. Once you see that the most reliable part of physics functions without offering an ontology, you cannot return to naive realism. You cannot pretend that deeper inspection will necessarily reveal deeper pictures. It may reveal deeper rules instead. If something is hiding inside the photon, it is hiding in the gap between what can be calculated and what can be said, in the space where prediction outpaces description. This gap is not a failure of science. It is one of its results. You are left knowing that light, the thing you depend on to see the universe, does not itself become visible when examined closely. It dissolves into mathematics, into probabilities, into structures that resist translation into experience. The messenger does not reveal its own nature, and that has consequences. It suggests that the universe may be fundamentally indirect, that access is always mediated, that what you experience is not the underlying structure, but the outcome of interactions shaped by rules you do not fully grasp. This does not make reality meaningless. It makes it conditional. Meaning arises from what can be constrained, predicted, and shared, not from what can be pictured. The photon has shown you this quietly, without drama. It did not violate laws. It did not announce a paradox. It simply refused to become simple. And now you are left with the question you cannot unask, not what is inside a photon, but whether the universe was ever made of things with insides at all.